Good morning, physicsy people. Really disappointed that you don't get to do these labs, right? So this week and next week, because this week will only be really new material Monday, Tuesday. Wednesday is just kind of a catch-up day, and I'm having difficulty with things, so I'm going to do a Google Meet from like 9 to 11 on that Wednesday. Would that be April 8th? So if you need help with something, that would be a good time to get that. Any afternoon is a good time to get that. But this series of labs I really like, but it's ones where the students do them for like 15 minutes or 20 minutes, depending on 30 minutes, even depending on lab. And then we talk about it and that kind of stuff. So I'll kind of recreate those a little bit. Then what I'll do is I'll post the questions for it, have you think through those questions, and then post another video with discussing the answers. So try and do the question part on your own. At least think through them. I don't care if you even write them down. Just think through them, then come back and watch the second video where I'm talking through those. So the first one today is on flat mirrors. This is chapter 13 in your book. Chapter 13, section 1 is just light characteristics. It's inverse square law. We've already done inverse square law for sound. Well, guess what? Light does it too. Light's electromagnetic radiation. We hit that quite a bit in chemistry, so I don't think we need to hit that a whole bunch more here. And how to calculate like the wavelength and frequency and the speed. Well, that's the same equations we've been doing and stuff. So anyway, I've got a flat mirror here. And the way this normally works is I have you do this on the table, and then you like have stuff standing behind it, and you match stuff over here. So you can see the where the light bends that way. What we're going to do instead is I'm going to use a laser pointer, and I'm going to try and have us like follow a path in there, right? So I'll do this first one. I'm going to try and have my angle come in here at 50 degrees, right? So if we make a dot right here and then a line at 50 degrees, so this angle right there is 50 degrees. So if we do that, right, without a mirror, right, it goes through like that. Without a mirror, and then if we go out here a little bit, we go through here, hopefully you would guess that if I measure this angle, what would we get, right? I don't know how well you can see that. Maybe I need to make that a little bit bigger. We're not going to have as clean angles and stuff there, but so if I put this here, hey, look at that, that's 50 degrees. So if it comes in at 50 degrees and there's no mirror, it's going to be 50 degrees on the other side too. So then if we look at a mirror there, so now I've got a mirror. I come in at 50 degrees, and now we see it bounces off the mirror. I don't know how well we can see that on there. My hand's in a bad spot for that. All right, so you see where that's at right there. I needed an extra hand. That came up right there. So if that came right there, this is some sloppy lab work, but at least it can give us some data, so I'm not just telling you everything. Well, yeah, that's really sloppy because that's at about 40 degrees, and that needs to be 50 degrees. That should be 50 degrees. I must be being a little bit sloppy here. Yeah, I guess I should be a little bit below that right there. Right? So the angle of reflection is the same as the angle of incidence. This is called the angle of incidence. That this comes in at 50 degrees, it should bounce back out at 50 degrees. I was a little sloppy. You can even see those aren't lining up quite nice. Right there, I was probably angled a little bit here and stuff too. A couple little mistakes can add up to a little bit bigger one. Right? So if I come in at a steeper angle, let's say 75 degrees. So that's 75 degrees. That's my central point there. It comes back out. Right? It's hitting my finger right there. So if I'm trying to get some slightly better data here. You really need a second set of hands, but I don't know how you do that with social distancing. think that's about the line it was making. Again, I don't know how well you can see that, but that is at 75 degrees there. So if this angle is 75 degrees, this angle is going to be 75 degrees. What they actually like us to do is you do a normal, which is 90 degrees perpendicular to the surface, and then we measure from there. That's really what we should do. That's harder to do on the board here, but really my angle of incidence is 15 degrees off of the normal, and my reflected angle is 15 degrees off of the normal. And we can see that. I don't think that's any massive shock to us or anything. If I go ahead and just do that down here, we can see when I have let me tilt it in just a little bit. When I have a fairly shallow angle, right, or pretty, right, so we can see this down here. How well can we see that? And then come in at like 90 degrees. We can see that, right? And the closer you get to 90, hey, look at that. And if I go 90, it comes right back out at me, right? So we can see the angle of incidence is going to equal the angle of reflection, as long as you have a nice smooth glass surface and all that kind of stuff. The way they make a mirror is just a piece of glass with a dark printing on the background. They used to use silver on the back. So if you remember your chemistry ornaments, when we made those, we did a reaction. It just made silver on the inside of those test tubes. You had glass and then you had silver. And so then the light would go through and it couldn't go all the way through, so it would bounce back out. Now they use plastic coatings and things like that because that's a lot cheaper and not silver and all that kind of stuff. So I will post some questions from the lab in the, I'll post those questions. Take a look at those, try and answer those, and then come back and do the second video where I answer the questions.